Welcome to The Explainer. Have you ever just stopped and wondered how we get these incredibly detailed pictures from inside the human body without a single bit of harmful radiation? Well, today we are demystifying the absolute magic of MRI. And if you're a medical trainee, think of this as your essential guide, your crash course in how we turn a tiny spinning proton into a picture that can literally save a life. Okay, so here's our game plan for this explainer. First up, we'll talk about why MRI is such a powerhouse in medicine. Then, we're going to dive into the really cool physics, what I like to call the proton dance, and figure out how we actually listen for the echoes that build our images. After that, we'll get into the hardware that turns those signals into detailed slices of the body, and how we can choose different views to find exactly what we're looking for. And finally, we'll bring it all home and connect everything back to what you'll see in your day-to-day clinical practice. So, what is it that makes MRI so incredibly special? I mean, this isn't just another scanner in the hospital basement. The science behind it was so revolutionary that its creators, Paul Lauterbur and Sir Peter Mansfield, earned the Nobel Prize for it back in 2003. Let's dig into why. Right here, this is the absolute game changer. You know, with CT scans or X-rays, you're always using ionizing radiation, which has its risks. But MRI, it gives us this unbelievably clear, detailed look at the body's soft tissues. We're talking brain, muscle, ligaments, organs, all with absolutely zero radiation exposure. For patient safety and our ability to diagnose, this was just a massive leap forward. All right, let's pop the hood and see how this amazing piece of technology actually works. Believe it or not, it all starts with the unsung hero of the MRI world, the humble hydrogen proton. And because our bodies are mostly water, these little guys are absolutely everywhere. So just picture it. Inside our bodies, there are billions and billions of these tiny spinning tops, protons, all just pointing in completely random directions. But then, when a patient goes into the MRI's super powerful magnetic field, we call that B0, a very small fraction of these protons snap into alignment with that field, kind of like tiny soldiers all suddenly facing the same direction. But they don't just stand perfectly still. They start to wobble or precess, just like a spinning top does right before it falls over. Now, this wobble is anything but random. It's actually governed by a beautifully simple but incredibly powerful rule, the Larmor equation. All this equation says is that the speed of that wobble is directly linked to the strength of the magnetic field it's in. And that, right there, is the secret sauce of MRI. It means we can tune in to these protons, just like tuning your radio to a very specific station. And this is where you see just how precise this whole thing is. For hydrogen, that Larmor constant is a known value, 42.57 megahertz for every Tesla of magnetic field strength. So, in a typical 1.5 Tesla scanner, we know for a fact that the hydrogen protons are all wobbling at about 64 megahertz. We know the exact radio station we need to tune into to talk to them. It's amazing. Okay, so we've got our protons all lined up and wobbling at a predictable frequency. That's great. But how in the world do we get them to tell us what kind of tissue they're hanging out in? Well, we send in a quick burst of energy, a radio frequency, or RF pulse, that's tuned to that exact Larmor frequency. You can think of this pulse as a little energetic nudge that knocks the protons sideways, out of alignment. But here's where the magic happens. As soon as we turn that pulse off, the protons start to relax and go back to where they were. And as they do, they release that energy they absorbed, sending out a tiny, faint signal, an echo that our scanner can hear. Now, this is where it gets really, really cool. This relaxation isn't a one-size-fits-all process. It happens in two different ways, and, critically, at different speeds in different tissues. T1 relaxation is basically how quickly the protons stand back up and realign with that main magnetic field. Tissues like fat do this really quickly. T2 relaxation is different. It's a measure of how quickly the protons get out of sync with each other after being knocked sideways. Imagine a group of synchronized swimmers who all start a move at the exact same time but slowly drift out of phase. That's T2 decay. And the simple fact that different tissues have unique T1 and T2 times is the entire basis for creating contrast in an MRI image. Okay, so we're getting an echo that tells us about the type of tissue we're seeing, but the scanner is picking up millions of these echoes from all over the patient's body at the same time. How does it know where each signal is coming from so it can build that beautiful, detailed map of our anatomy? To answer that, let's pull back the curtain and look at the actual hardware. This is how the scanner takes millions of those tiny whispers from protons and turns them into the incredibly detailed images we rely on every single day. The real genius behind locating each signal is a piece of hardware called the gradient coils. The best way to think about them is as a GPS system for the body.
By creating tiny, predictable variations in the main magnetic field, they make it so that protons in your head are wobbling at a slightly different frequency than protons in your feet. By carefully manipulating these gradients, we can assign a unique frequency address to every single point in the body. That's how we map the origin of every single echo. It's brilliant.
So, now we can create a signal, and we know where it's coming from. Now we get to the really fun part. How do we manipulate that signal to highlight exactly what we want to see, whether that's healthy anatomy or some hidden pathology? We do this using something called a pulse sequence. You can just think of it as a recipe of RF pulses and gradient changes. Now, the two key ingredients in this recipe are TR, or repetition time. That's how often we send in an RF pulse. And TE, or echo time. That's how long we wait before we listen for the echo. And as you can see here, by just playing with the timing of TR and TE, we can weight our images to emphasize either the T1 differences or the T2 differences between tissues.
So if you remember one thing as a clinician, let it be this. T1 weighted images are for anatomy. In a T1 image, fat is bright and water is dark, and you get these beautiful, crisp pictures of the body's structure. T2 weighted images, on the other hand, are for pathology. On these scans, water is bright. That means things like swelling, inflammation, or tumors. Anything with high water content will light up like a Christmas tree, making them incredibly easy to spot.
All right, let's bring this all together. We've talked about the physics and the hardware, so let's finish up with what you really need to know before you order an MRI for your patient.
Okay, first things first, safety. Before anyone gets near that powerful magnet, a thorough screening is absolutely non-negotiable. We're talking about things like older pacemakers, certain types of metal implants, or any metal fragments in the body. Those are a definite no-go. But you also have to think about the practical stuff. Is your patient stable enough to lie still for a long time? Are they claustrophobic? Because even the tiniest bit of movement can completely ruin an image.
And just like in CTs, sometimes we need a little extra help. And that's where contrast agents come in. For MRI, we typically use gadolinium. What it does is shorten the T1 relaxation time of tissues. So on a T1 weighted image, areas that have increased blood flow or a breakdown in the blood-brain barrier, think tumors or active inflammation, will soak up that gadolinium and become much, much brighter, helping us to zero in on exactly where the problem is.
And that really brings us to what's next. We're already seeing machine learning and AI dramatically speed up scan times and clean up images that used to be ruined by patient motion. The power of this technology is just constantly evolving. It really makes you stop and think, what incredible new diagnostic doors is MRI going to unlock for us in the next 5 or 10 years? The possibilities are pretty exciting.